Hey guys, we're going to talk today about antiderivatives. So you guys should have a pretty good understanding of the derivative. So now let's talk about if you're given a derivative, how you can get back to the original function. So we have a definition here that kind of defines your antiderivative, and it defines it in terms of an indefinite integral. So this thing right here is called an indefinite integral. And the indefinite integral calculates the antiderivative plus some constant. And so we have to have this constant there because remember, if you differentiate a function with a constant hanging out on the end of it, it's just going to become zero. So when we find the antiderivative of a derivative, we don't know if it has a constant there or what the constant could be. So you always have to remember that anytime you calculate an indefinite integral, that you have to include that constant at the end. All right, so let's look at some basic rules for antiderivatives. And they're pretty simple. You just have to think about derivatives but going backwards. So here is what's called the power rule. And so instead of us bringing our value down and subtracting 1 from it, we bring the reciprocal of 1 plus our power, and that goes in front, and then we add 1 to the power. So here's a really easy example. So say we have um, x squared as our derivative, and we want to find the antiderivative. Then this would just be 1 over 2 plus 1 x to the 2 plus 1 plus c, which would be 1/3 x cubed plus c. Now you can always check your work if you differentiate. So if we differentiate this thing right here, then we end up with 3 times 1/3 x squared. The c is just going to be 0. 3 times 1/3 is 1, so that just gives us x squared. So you always get back to where you started. So let's try this example down here, see if we can apply the power rule. So the first thing I always do, kind of like when you differentiate, is I always take and write all of my, see this fraction right here, that right there, I want to write all those just with exponents. So I want to rewrite this as x to the 1/2 power plus, and then I want to write this as x to the negative 2 power minus 3x to the 4th dx. And then I can just evaluate each one separately. You can kind of distribute the integral symbol across addition. So this becomes 1 over 1/2 plus 1 x to the 1/2 plus 1 plus 1 over negative 2 plus 1 x to the negative 2 plus 1 minus 3 over 4 plus 1 x to the 4 plus 1. And don't forget your c. So now we just clean up a little. 1/2 and 1 is 3/2. If I take the reciprocal of that, I get 2/3. So this is 2/3 x to the 3/2 plus. This now becomes 1 over negative 1, so that's just a negative x to the negative 1. And then this becomes negative 3/5 x to the 5th plus c. And that's it. I'm like, no, I think that's good. And there's my antiderivative. And I could always check my work by differentiating and checking to make sure that I get what I'm starting with. So let's try a couple more rules. So a really neat one, just like how neat the derivative is that the derivative of ln x is 1 over x. Now we put these absolute values here because of the fact that you can't take the natural log of a negative number. So it's just kind of a restriction on the domain. So then if we take the antiderivative of 1 over x, or I've written it a little differently for you here, we get ln of x. Let's go back. So it's pretty simple. I have an example for you. Excuse me. So I have a 10 on top, and I want to rewrite this by bringing the 10 out front like it's a constant. We can do the same thing when you differentiate. If you have a constant times your function, you can just bring it out front. And then this becomes 1 over x dx. So then this becomes your constant. The antiderivative of 1 over x is ln of the absolute value of x plus c. All right, so now let's talk about trig functions. So I have something a little different here. Now we have our basic trig functions, like the antiderivative of cosine x dx is just going to be equal to sine x dx. So I don't really see, or sine x, sorry, plus c. So I didn't see a need to list all of those for you because they're just the opposites of your derivatives. The antiderivative of sine is negative cosine. So, and sometimes you have to flip-flops the positive negatives to make sure that everything takes care of itself. But on here, what happens if you want to take the cosine of some linear transformation where you have a constant times x plus maybe another constant? This is pretty simple, and it's almost like using the chain rule backwards. But kind of to account for the fact that if you differentiated this function right here, that it would be k times sine or cosine of kx plus b. So kind of to counteract that, we have to multiply by the reciprocal of k. And this is always just going to be by the reciprocal of the number in front of x. The b here doesn't really matter because if I were to differentiate the inside piece, the b is a constant, and so the derivative of that would be 0. This rule, similar rule, also for linear combinations, also applies. I'm going to flip over for a second. I'll do both of the examples to this neat little function e to the x. So if the derivative here of e to the x is e to the x, the antiderivative of e to the x is e to the x. How beautiful is that? Now, if we have a linear combination as our exponent, then it works the same way. If we were to take this right here and differentiate it, then we would have to use the chain rule. So in order to kind of account for that, we multiply by the reciprocal of k in front, because if we were to differentiate this piece right here, then this derivative would just be equal to k. So to kind of counteract that, we multiply the antiderivative by 1 over k. So let's take a look at both of these examples where we're using this linear transformation. Oh, oops. So let's look at the trig example first. So I have the antiderivative of sine of 2x minus 1 dx. So if I think about what derivative is equal to sine, well, I think, well, the derivative of cosine is equal to negative sine. Then the antiderivative of sine is going to be negative cosine. And so I always leave what's inside these parentheses there. So this is going to be 2x minus 1. But to account for the chain rule, I multiply the front by 1 over 2. And then don't forget your c. And I can't clean that up anymore, so that's just my answer right there. So let's try one with e to the x. So here I have e to the pi x dx. So this is the same deal. I have a constant in front of my x multiplied together. So in order to balance the chain rule, this is going to be 1 over k. My k is just pi. E to the pi x plus c. Now we actually have a method for determining what c is if we are given a point on the antiderivative. So if we're given a point, we can use it to solve for c. And so what we would do is we would find the antiderivative. So let's write down some stuff. In this case, we are given a derivative. So in this example, we're given dy dx. So when we find the antiderivative, it's going to be y is equal to some function in terms of, oh, I apologize. I made a mistake here. If that's t, then this should be t also. So we're going to end up with some function y in terms of t. So then what you want to do is you want to plug in the point. you're given and solve for C. And then, of course, rewrite so that you have the actual antiderivative with C plugged in. So let's first find the antiderivative. So I'm going to just kind of integrate, that's how I would think of it, both sides of my equation. The integral of dy dt is just y. And then the integral of 2t plus 9t squared, so I'm going to use the power rule. So this is going to be 2 divided by, the exponent on t is just a 1, so 1 plus 1 t squared plus 9 divided by, and then my exponent's 2, so it's going to be 2 plus 1 t to the 2 plus 1 plus c. So let's clean up some. So then this will become 2 divided by 2 is 1, so this is just t squared plus, this will be 9 divided by 3, so that's 3t cubed plus c. And then this is equal to y. So then they tell me that when t is 1, y is 2. So I can plug this in. So I get 2 is equal to 1 squared plus 3 times t is 1, 1 cubed plus c. So this is going to be 1 plus 3, so that's going to be 4. So if I subtract 4 from both sides, I get negative 2 is equal to c. And now I can rewrite my antiderivative. I get y is equal to t squared plus 3t cubed minus 2. And there is my solution. You would actually call this a solution to a differential equation because we started out with a derivative, and that equation is called a differential equation. And then when we're able to solve it for y, that would be our solution. And you can have lots of solutions to a differential equation, but this is a particular one because we're given an initial condition. And so it's just one solution. Okay, well, I hope you guys get some good practice. Thanks so much, and I'll talk to y'all soon.